All right, so today we're going to begin a new topic that we're going to discuss for a good portion of the semester. So that being said, just make sure that you really watch and rewatch this video to make sure you fully understand. But we're going to introduce the topic of the derivative. But before we do that, I want to review you on a couple of geometry topics, which I know sounds weird. But we're going to be referring to something called the tangent line, and that's a line that intersects a curve only once. Okay, so let me show you an example of that. So let's say you had a curve that looked like this. Okay, now if I asked you to find the slope of that curve, that would be a challenge, right? Because the slope here where I'm pointing is much different than, say, the slope here where I'm pointing now, or even here where I'm pointing now. So a lot of times we will look at what we call the tangent line. So let me draw just a random point there. The tangent line will be the line that kind of skims the surface, hits it once, and that's it. This is an example of a tangent of this curve. But the tangent will look much different if, say, we look at it from this point. So this would be the tangent to the curve if we moved the point around like that. So just know that the tangent is not unique. There are many, many different types of tangents, okay? And the reason we're going to look maybe at this is it's a lot easier to tell the slope or the rate of change of this red line, since it's a straight line, right, than this green curve that goes up and down and changes direction and all kinds of stuff. So in your algebra class, you probably discussed towards the beginning of the semester what slope was. So slope is always rate of change. The formula for slope is the difference between the y's over the difference between the x's. Okay? And that's for the slope of any line. So while a tangent is a line that hits a curve or intersects a curve once, a secant is a line that intersects a curve twice. So let's say we just had a basic parabola-looking shape. Okay? The secant would take 2 points, randomly chosen, and would draw a line between those two. And again, I'm not going to draw another one, but there are infinitely many secants as well. It just depends on where you have your 2 points drawn. So we're going to come back to the concept of tangent and secant towards the end of this lesson. But for now, I just wanted to define what those were. All right, so what this section is titled, and the topic that I told you we would be revisiting quite a bit this semester is what is a derivative? Okay, so the first derivative, okay, because we can have other numbered orders of derivative later on, but for now we're just talking about the first derivative. If you want the derivative of a function f of x, it is written as the following. So this is like a notation. You need to learn how to write it. You write it as f and then kind of a little slash mark slash apostrophe there. It's not the number 1. You literally read this as f prime of x. Okay, but what is it? That's what we want to talk about. So what would that derivative be? Well, it's an equation for the slope of the tangent line at that point. And so often when we have real-life scenarios where they're being modeled by an equation, the graph for that equation might be really varied and might be really curvy, like this one up here where we talked about tangent. Okay, so in general, the gist of this is that the derivative is the slope of the tangent line at any indicated point. Okay, and it turns out the equation to find this derivative or this slope is similar to the slope formula, but with kind of a calculus flair on it. So this is a formula that you're going to want to start committing to memory, but we've actually already looked at this a couple of sections ago. We just didn't define it as the derivative. So the formula for derivative of any function is always f of x plus h minus f of x all over h, and then you take the limit as h approaches 0 of that function. Okay. And just so you know, this is also what we would call the instantaneous rate of change. And we're going to compare that with another type of rate of change rather here in a little bit. Okay, so because this formula looks ugly, and remember we did this, I believe, back in section 10.1, this book and lots of calculus books use what we call a 4-step method for finding the derivative. Rather than trying to tackle this whole big ugly equation, all in one swoop, we like to split it up into manageable pieces, and that's all the 4-step method really is. So the first step is, rather than trying to find that whole thing, we're just going to try to find the f of x plus h portion. Okay, the second step is to take what we got in step 1 and kind of add in another piece to that big, long formula I need. So the second step is to find just the numerator of this fraction up here. So f of x plus h minus f of x. The third step is to complete the fraction. So you take what you got in step 2. Notice I'm just repeating a lot of what I did before, and then all of that over h. And then I'm going to put a star by this step. This is the whole thing. Okay, so finally you're going to now take the limit of step 3. The limit as h approaches 0 of whatever it is that you get. So I'm going to demonstrate this 4-step process throughout the lesson today, but just know that if you're pretty algebraically confident, you might not need to show all the 4 steps. The most important step is obviously that 4th one because it includes the whole formula, right? The formula for derivative is what step 4 is, okay? But notice these 4 steps are just starting off baby steps, right? We start off with a small piece of it. We put in a little bit more of the problem. Then we put it all over h, and then finally we've got the whole thing, okay? So, all right, so let's look at a couple functions. The first one we're going to do is going to be kind of on the easier side. It's not really that interesting of a derivative, just to be real honest, but it'll kind of get our feet wet with this process. So let's say we have a function 2x minus 7, and I ask you to find f prime of x. Okay. Now when you see f prime of x, that means I'm asking you for the derivative. Okay, so I'm asking you to do that long equation. The limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, that's what I'm asking for. Okay, and again, the 4-step process is just going to say, hey, I don't want to tackle all that at once, so let me just tackle this piece. Okay, we've done this before, okay, a couple lessons ago. But remember, f of anything just means, hey, go to your f equation and stick that in, right? So instead of 2x minus 7, it's going to be 2 parentheses minus 7, okay? Don't forget to use your distributive property. So from step 1, I'm going to get 2x plus 2h minus 7. Notice none of those are like terms, so that's like as far as I can go with step 1, okay? So step 2, you take what you got in step 1 and you subtract off f of x. Okay, so don't reinvent the wheel here. You already figured out what f of x plus h is, so we're just going to insert that. So 2x plus 2h minus 7. And now we need to minus whatever f of x was. Okay, so notice f of x just means, hey, go to the original and plug that in, right? F of x is 2x minus 7, according to the problem you were given. So this minus sign is going to distribute. So I'm going to end up with 2x plus 2h minus 7, and then if I distribute that negative, minus 2x plus 7. Okay, so much like the problems from about a week ago, notice that we're going to get pairs of things to cancel out. So 2x minus 2x is 0. Negative 7 plus 7 is also 0. That leaves only 2h. Okay, so now we move on to step 3. Which step 3 is do the same thing we did before, just put all of it over h. So we're going to take the 2h and we're going to put it over h. Okay, but notice what happens here. We have an h in common, right? Only one term on top and bottom. And so we end up simply getting a 2 here. So the last most important step is where you do the whole thing. So the limit as h approaches 0 of that function, right? So notice this is just going to give me the limit as h approaches 0 of 2. And notice, normally speaking, if we had an h here, we would replace h with 0, but we don't even have an h here, so the answer here is just 2. Okay, so f prime of x for the function f of x equals 2x minus 7 is equal to 2. Okay, so pretty early on, I want you to make sure you understand the significance of this. So this is the slope of the tangent line. Okay. By the way, the reason I said this problem was not that interesting is notice the original function, if we were paying attention, the original function was a line, right? It was linear. And so what's always going to be the slope of this line, no matter where you look at it, no matter where the point is located on that line, notice the slope will always be 2. Okay, and notice that's the answer that we got here when we did derivative. Okay, so that's what I meant when I said it's really not that interesting, because it's actually a steady function. The slope of that tangent line is always 2 because it's just a line to begin with. But when this question is much more interesting is when we have something that is not linear, like maybe something like x squared plus 2. And again, I want you to find the derivative. Okay. So the first thing is I just want us to sketch, or maybe you can look. Okay. Here's the graph of x plus 2. It's a parabola shifted up 2 units. Okay, so notice, if I tried to ask you what the slope of this curve is, that would really depend, right? It would depend on whether I'm talking about this location, okay, because this location has a slope of about something like that, right? It has a negative slope, okay? Whereas if I asked you about this point location, it would have a positive slope, right? So we don't have a steady slope like we did in example 1. In fact, we're going to have varied slopes. It's going to depend on what point we're at as to what our slope is. So the formula for derivative is, again, this long fraction. While you're learning it, it's probably best if you go ahead and write out that function every time, just so you can kind of learn it. But step number 1 is to find just this piece. So we want to go to our f equation and we want to replace x with what the parentheses is, which is x plus h. Okay? So we're going to do x plus h parentheses squared plus 2. Okay? Notice the structure of the original and this are the same, right? It's just this parentheses squared plus 2 instead of x squared plus 2. Okay? So I think we've talked about this before, but remember, you are not allowed to distribute an exponent when you're adding or subtracting. Okay? So instead, you're supposed to be thinking of this like something times itself. That's what something squared means. In other words, make sure you use FOIL here. Okay? Because if you FOIL this, you're going to get x squared plus xh, right? First times first is x squared. Outside, x times h is xh. Inside would be h times x. So I'm going to write that as xh again. Okay? And then last, h times h would be h squared. Don't forget about your plus 2 right here. Okay? So notice we do have some like terms. These two are like, right? So we end up with x squared plus, we have one of these things plus one more, so that's a total of 2. And then plus h squared plus 2. Okay? I'm going to circle that because step number 1 is done. Notice none of these are like terms. I can't combine x squared with 2xh or with h squared or anything like that. So time to move on to step number 2. So for step number 2, we're going to take what we just got in step number 1 and we're going to subtract off the original function. So what I just got was x squared plus 2xh plus h squared plus 2. And I'm going to subtract off the original function, which was x squared plus 2. Okay, it's always what we got in step 1 minus the original function. Okay, and then just like example 1, that minus sign is going to come through and change the signs. So I'm going to get x squared plus 2xh plus h squared plus 2. Notice nothing happens to the first parentheses, but the second parentheses, both things will change sign, which gives us a couple more pairs. So x squared minus x squared is 0. 2 minus 2 is 0. So what we have remaining after step 2 is just 2xh plus h squared. Okay, they're not like terms, so we're done with that step. So step 3. By the way, when you're doing this, if you use this method on a test or something, make sure that you write out these left-handed steps here, because these are not equivalent, right? I'm getting much different things in steps 1, 2, and 3, so you don't need to just do this all together and write equal signs between the steps, because the steps are different results. So now we're going to take what we got in step 2 over h. Okay, notice just like in number 1, now we have something in common between everything, right? We have an h that can cancel. Notice here there are 2 h's, so it would only cancel one of them. So what is remaining after I cancel h's is 2x plus h. And then last but not least, the whole thing is the limit as h approaches 0 of f of x plus h minus f of x all over h. So we want the limit as h approaches 0 of 2x plus h. Okay, so notice at this point we no longer have a fraction where we would have to worry about 0 being plugged in and giving us a denominator of 0. So now we're going to plug in h equals 0. Okay, and so our final result is 2x. So if we want to write it in function notation, the derivative equation is 2x. Notice I didn't get a number this time, and often you won't for the derivative. Okay, but this is the equation for the slope of the tangent at any point. Okay, don't mistake this to mean that the slope is 2. Okay, the slope is 2 times whatever x is at that particular point. Okay, so let me kind of demonstrate what I mean by that. Let's take some examples and see if we can find out what the specific slope would be at various stages along that curve. So I want to kind of do a part B here. All right, so I want you to tell me what is the specific slope. So what is the slope of the tangent of f of x equals x squared plus 2. Notice that's the same function as I asked you about in part A, so I'm not changing anything. For the following, what if x is 4 versus what if x is 0, and then what if x is negative 3? Okay, so by the way, our slope equation, let's go ahead and rewrite that since we may not be on screen anymore. This is what we got for our answer in part A, right? The equation for slope is 2 times x. Okay, so for the first x value, if I want to know the slope, let's use the letter m for slope like we did in algebra. Okay, the slope is going to be 2 times whatever x value you are given. Notice I'm given an x value of 4. So the specific slope when x is 4 is 8. If you change the x value like we do here, okay, notice the slope will change also, right? So if we want the slope when x is 0, it's still following this pattern or this equation, right? So it's going to be 2 times 0 or a slope of 0. Remember what kind of lines have slopes of 0? It means that the tangent line is horizontal at that spot. And then finally here, we'll do 2 times the x value, which is negative 3, and we'll get negative 6. Okay, so all of these are different slopes that occur along that parabola because it depends on where are we located in the curve that tells us kind of what the slope will be. Okay. Okay, so let's do another one maybe with an x squared original equation. Okay, you are going to need to keep your algebra skills on hand here. I mean, you're going to have to make sure you know how to do things like foiling and distributive property and keeping signs straight and all that stuff. Okay, So let's say that g of x is 2x squared minus 5x, and I ask you to find the derivative. Okay, notice I switched to g. It doesn't really change anything other than all the things that were f will now be g. So it's g of x plus h minus g of x all over h, and then take the limit as h approaches 0 of that. So just like before, I'm going to tackle pieces at a time. Okay. Step number 1 is often one of the more difficult steps to this 4-step process. Okay, so if you can get past the tediousness of step 1, then you pretty much have it, because then things start to cancel out. So notice if I want g of x plus h, that means come back up here where I'm pointing and plug x plus h in for both h, or both x's rather. So this would be 2 times parentheses squared minus 5 times parentheses. Okay, so there's kind of a lot of algebra to keep straight here. So here we get x plus h times x plus h times 2, right? And then minus 5 times x plus h. So again, I need to FOIL here. But if you notice, I'm going to cover up the 2 for a minute. We already did this exact FOIL process in the previous example, right? In fact, everything that has an x squared, you're going to end up with this step somewhere along the way. So it's probably best if you just go ahead and kind of remember what that foiling was, okay? So in other words, we're just going to use the previous example. What did we get when we FOILed x plus h times x plus h? Well, we got x squared plus 2xh plus h squared. Okay. So now I think I'm ready to distribute. So notice this 2 is going to go to everything, but then so is this minus 5 going to go to all the second parentheses data. So I'm going to get 2x squared plus 4xh plus 2h squared, right? Because we double everything, right? 2 times everything. And then minus 5 times x is minus 5x. Minus 5h is minus 5h, okay? So we may not love it, but there are no like terms here. Okay, there's nothing you can do with that. You're just going to have to temporarily be okay with the fact that we have a lot of terms there. So time to move on to step number 2. Remember, it's step number 2 that often begins the simplification process. Lots of things start to cancel out, and that's kind of the benefit of that step. So let's pull down what we got for the g of x plus h part, which was all of this, right? Everything I got in step 1. And now I want to subtract off my original g of x, which was this. Okay, so definitely don't forget that the signs change, okay, but maybe we don't need to write that out again. In other words, if we can see that this is 2x squared minus 2x squared once we distribute, then we can go ahead and get rid of those. If we can see that this is going to be minus 5x plus a 5x by the time we distribute that negative, we can go ahead and get rid of those. And so what we're left with is 4xh plus 2h squared minus 5h. That's all that's left after step number 2. Okay, so step number 3 is take step number 2 over h. So I'm going to take 4xh plus 2h squared minus 5h and put that all over h. Okay, so notice again, kind of a common process, right? In step number 2, often pairs of things get canceled. In step number 3, we are almost always canceling the h's out. So notice everything has an h. Okay, just be careful about that, right? This is h squared, so there's still an h there. So what would be remaining is 4x plus 2h minus 5. All right, so lastly, and we should have our result, the limit as h approaches 0 of g of x plus h minus g of x all over h would be the limit as h approaches 0 of what I just got in step 3. Okay, so notice now we are free to plug in 0. And notice when we do that, the middle term goes away, right? So we're just left with 4x minus 5. So g prime of x is 4x minus 5. Okay, and I know I'm continually kind of having you write this down, but this means, remember, that this is the equation for the slope of the tangent line. Okay, so again, the slope of the tangent is not 4. Okay, it's 4 times whatever x value you're at minus 5. Okay, so let's practice a few of those. Let's see if we can kind of squeeze it in. So I want you to find the slope at the following 2 spots. So what about at the spot 0, 0? Okay, notice this time I gave you a full point rather than telling you what the x value is, but all you need to do is pull the x value out. So notice here x is 0, okay, so the slope is going to be m equals, and you're going to plug 0 into this slope equation, so it's going to be 4 times 0 minus 5, or a slope of negative 5. So the specific slope that the tangent line has at this spot is negative 5. But not surprisingly, if we switch the point, okay, so let's maybe take the point 1, negative 3. Notice here x is 1. So the slope is going to be 4 times 1 minus 5, okay, or negative 1, right, because 4 minus 5 is negative 1. And notice, if I were to ask you about other x's, all you do is plug that x value into this equation that you just found for slope. Okay. Okay, so let's go back to what the derivative just kind of is in general. Remember, the derivative is a slope, right? It measures a rate of change. Okay, and there's lots of data and numbers in the real world that we like to have the rate of change for, right? If you are a business owner and you're trying to track your profits or track your revenues or track your sales, you'd probably want to know what the rate of change of those profit, sales, or revenue is, right? And that wouldn't necessarily stay steady every year, right? That would be a value that was probably consistently changing from year to year. So I mentioned this before, the fact that the instantaneous rate of change was kind of equivalent to the derivative. Okay, so the instantaneous rate of change is the slope of the tangent line. Okay, I know I already mentioned that, but we're going to contrast that with something else. So the formula is what we've been doing for the past few examples. The limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so notice that's a familiar formula, right? We've been working on that already. Okay, but let's talk about in real life what it means to be an instantaneous rate of change. Okay, so if you are driving in your car to work or to school or whatever, your instantaneous rate of change for your drive would be the speed your car is traveling at any given time. Notice that would be different, right? Like if I'm traveling to work at 8 o'clock, my speed, when I look at my speedometer at 8 o'clock, is likely very different than my speed at 8:15, right? Or at least different, right? Maybe not very different, okay? But it's not a steady thing, right? It would depend on the time of, or what time in your journey you were at, right? So if I look down at my speedometer today on my way home from work, I wouldn't expect that that would always stay the same, right? But my instantaneous rate of change would be any time I look down at my speedometer, that would be the rate of change for that instant, okay? So let's compare that to average rate of change, which we haven't really mentioned much of today. So the formula for average rate of change is very much like the one for instantaneous rate of change. Just hopefully you notice that it's missing something, okay? So notice it's a slope formula without the limit part, right? So we don't have the limit as h approaches 0, okay? We talk about this as the slope of a secant line. So remember back when we showed our pictures at the beginning of this lesson, it was the slope between any 2 points, right? So the difference between a real life application here is this would be like the average speed of your car over a time span. So the average speed of your car during your entire commute. So notice I might average, 70 miles an hour for my 30-minute commute, but that doesn't mean that I went a steady 70 miles an hour. It means likely sometimes I was going faster and sometimes I was going slower, and then maybe sometimes I was going exactly the 70 miles an hour that I mentioned. Okay, so this is not going to be much more difficult to find as long as you understand what the formula is. Okay, so the first thing that I want us to do for this one, so let's say f of x was 3x squared. Okay, the first thing I want you to do is to find the slope of the secant line. Notice that's different than I've been asking you for in the last few examples, right? Okay, so the formula for the slope of the secant is f of x plus h minus f of x all over h. But if you think about it, this is actually going to be easier than the instantaneous rate of change or than the derivative has been, right? Because it just is missing step 4, right? We get all the way down to step 3, and then we don't have to do the final step of finding the limit as h approaches 0. So of the 4-step process, we're basically going to still do 3 steps of it. We still want this equation, and we're still going to break it down into baby/more manageable pieces. So if I want f of x plus h, then I take my f of x and I plug in x plus h, right? So just like before, I'm going to need to make sure that I FOIL. But like I mentioned back on example 3, we've already FOILed this, okay? So again, I think you can see the merit for maybe just memorizing what this would be, but this is x squared plus 2xh plus h squared for the FOILing part. And then I'm going to distribute that 3. Multiply through by the 3, in other words. So if I do that, I get 3x squared plus 6xh plus 3h squared. Okay, so step number 2. Now that I'm finished with step 1, I'm going to take what I got and subtract off the original. So this is going to be 3x squared plus 6xh plus 3h squared, what I got in step 1, minus the original function, which was a pretty simple one, right? Just minus 3x squared. So notice, as usual here, 2 things are going to get canceled, right? And that's going to leave me with 6xh plus 3h squared. And now, finally, let's put everything over h. And again, I won't need to do step 4 because the equation for the slope of the secant, it does not include that limit portion. Okay, so notice h's are gone. So I'm left with an equation of 6x plus 3h. Okay, so rather than the slope of the tangent, notice this is the slope of the secant. Okay, so let's look at maybe some more facets to this problem. Okay, so let's say that I asked you to find the following. Now I want you to find the slope of the graph at 1, f of 1. Okay, so this is the format that your book likes to put this in, and I think it's maybe a little overly confusing just in the notation that they use. Try not to get too worried about this. This is an x, and f of something is always a y. So all they're saying is that x is 1, and that y is whatever you get when you plug in 1. Okay, so if we want to kind of figure out what that is, let's go ahead and plug in f of 1, or plug in 1 rather. So 3 times x squared. It looks like y is 3 when x is 1. Okay, so really what this is talking about is the point 1, 3. Okay, and I think we'll like that structure better. All right, so let's talk about what the problem asks for. It asks for the slope at a certain point. Okay, well, we have a formula for slope. The formula for slope is this derivative formula. The limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, but remember, we already did steps 1 through 3 of this, right? Like, we don't need to redo it. We don't need to reinvent the wheel. So we already know that what we really want here is the limit as h approaches 0 of what we got above, which was 6x plus 3h. Okay, so notice now we're going to plug in h equals 0. And so we get a slope equation of 6x, not a slope of 6, but a slope equation of 6x. Okay, so finally, to answer the question, I'm going to squeeze this in over here. If I want to know the slope when x is 1, okay, then I need to do m equals 6 times 1. So notice the slope did end up being 6, but it's only because I was asked about an x value of 1. If I would have been asked, for instance, about an x value of 2, then the slope would have been 12. Okay, 6 times 2 is 12, right? If I would have been asked about an x value of 3, then the slope would have been 18 because 6 times 3 is 18. Okay, so just remember, and again, I'm not trying to keep repeating myself, it's just this is really, really important. This is the slope equation. This is not the slope specifically, right? Because the slope will change depending on what the x value is. All right, and then last but not least for this one, and then we're going to look at a business application to this real fast. So then what if I asked you to tell me the equation of the line through 1, f of 1, okay, which we already decided this was just an x and a y, right? So this is actually not really a calculus question at all. This is an algebra question. So one of the forms of the equation of lines that we learn in algebra is the point slope form, which looks like the following: y minus y1 equals m times x minus x1. And then I just need to figure out what to plug in where, right? Like, I know all these values if I go back to step B. Okay, so it's y minus the y value at that point. Okay, so look up here. Okay, let me slide this back down. Notice my y value is 3, right? So it's going to be y minus 3 equals the slope that we got in step B, which was 6, times x minus the x value, which is 1. So if you distribute this 6, okay, and then if you add the 3, so we'll get y minus 3 equals 6x minus 6. And then we'll add 3 to both sides. So we've got y equals 6x minus 3. Okay, so that would be the equation of the line through the point 1, comma 3. Okay. So definitely kind of some algebra review for you for sure. All right, so let's look at maybe an average rate of change problem that involves a business topic like maybe revenue. So let's say that you have a business that you're studying or that you work for, and their pattern for revenue looks like this function, 60x minus 0.025x squared. And I want you to find the average rate of change if sales go from 1,000 to 1,050 units. Okay, by the way, that rate of change is going to be different depending on what unit numbers you're going from and to. Okay, so 1,000 to 1,050 units is a significant detail of this problem. So I'm going to underline what it's asking for. It's asking for average rate of change. Okay, so here's my formula for average rate of change. Remember, average rate of change is that long formula, just not the limit part. Okay, but what I really want you to see is this is just a slope formula. Okay, notice this is the difference between two y's, right? F of x is always the y. And then even h is the difference between the x's. Okay, so that's what h is equal to. H is equal to the change or the difference between the x's. Okay, so let's look at the average rate of change formula and see if I can figure it out. Okay, so for the average rate of change, I'm going to change the letters to be appropriate for this problem. So this is what the average rate of change would be. It would be the revenue at 1,050 units minus the revenue at 1,000 units. Okay, notice f of x is where we started with, right, the 1,000 units, and f of x plus h is where we started plus a little bit more. Okay, and then what would this go over? So you need to decide what h would be. So h is the change we're making, right? So you can either write it like this, or you can go ahead and work that out in your head or something, but the difference between 1,050 units and 1,000 units is 50. Okay, so that's what we're going to have there on the denominator. Notice we still need to know what these two values are, right? But we can use our calculator to get that. So I want to know what r of 1,050 is, but also what r of 1,000 is. So go back up to your original revenue equation. It's 60 times x minus 0.025 times x squared. And then same thing here. 60 times x minus 0.025 times x squared. Okay, so you'll want a calculator for this. So see if I can project it so I can kind of show you some pointers on that. So let me see if I can get it to where you can see it. All right, so 60 times 1,050 minus 0.025 times 1,050 squared. Okay, so notice this gives me a value of 35,000. I'm going to move it back in a minute. 437.50. Okay, so now I want to enter in the same equation for 1,000. So one of the keys that you can use, you can go second enter on your calculator, and notice it repeats the same thing that I typed in, but it allows you to use these. Notice how my black bar is moving. It allows you to use these arrows to kind of edit, because notice I want the same look of the function, right? I just want to change all the 1,050s to 1,000 instead. Or you can enter it all in fresh again. Either way is fine with me. But you just get plain old 35,000 here. Okay, so now we have everything we need, right? We've got the average rate of change formula. So the average rate of change is this 35,437.50 minus 35,000, and then over the 1050 minus 1,000. Okay, so work all of that out, but if you work out the top, you're going to get 437.50. If you work out the bottom, you're going to get, of course, 50. And if you were to divide those, you're going to get 875. Okay, so let's talk about the significance of this 875. Okay, this is a rate of change. Okay, so this is the rate of change of the revenue per unit. Okay. By the way, the fact that it's positive indicates that our revenue is increasing at this point. Okay, if we would have gotten a negative rate of change, we can't have a negative revenue, but we can certainly have a negative rate of change for that revenue. That would indicate that the revenue was decreasing. Okay, so basically, whatever it is we're making here, every single time we make a new item after 1,000 units, between 1,000 and 1,050, we're gaining $8.75 for our business. All right, so the last thing I want to kind of put at the end of these notes is I want to review for you how you should have learned how to graph piecewise functions in algebra, but I understand that that might not have been something that your teacher taught you. So just to make sure everybody's on the same page, you might ask, like, what do you do when you have these functions in pieces and you don't have a graph for them and you would like one? Okay, so I'm just going to show you a brief example. You can always Google search more of these options if this is shaky for you. So here is what a piecewise function looks like. We've already discussed piecewise functions this semester. So let's say that it's x squared plus 1 if x is less than 0. but then the pattern is just plain old 1 if x is greater than or equal to 0? Okay, so what we have is a graph in pieces. Okay, and so what we're going to do is we're going to come up with 2 different tables of values for the 2 pieces. Okay, so back in algebra, when we don't know what a graph looks like, one fail-safe way to figure out what the graph is just to pick some x's, plug them in, and see what we get for the y's. Okay, so this first table, I want to be for only x's that are less than 0. Okay, so let's think of some things that are less than 0. -2 is less than 0. -1 is less than 0. Okay, so let's go ahead and go with those first, and then we're going to talk about maybe one more value that we want. So if you plug in -2 up here, you're going to get -2 squared, which is 4, plus 1, which is 5. Okay, if you plug in -1 here, you're going to get -1 squared, which is +1, plus 1, which is 2. Okay, I'm going to go ahead and note, though, this is just plain old greater than, by the way, so that means there's an open circle here. But we need to know where that open circle is, so I am going to plug in 0, but I'm going to make a note for myself that this is where an open circle would be, right? And it's an open circle, again, because this is just plain old less than. So if you plug in 0 here, 0 plus 1 would be 1. Okay, I just need to realize that, hey, that's going to be an open circle when I graph it. So let's graph this piece first. Okay, so I want you to maybe go out maybe 5 in every direction. You don't really need graph paper here. We can just sketch it. So I want to plot these points. Okay, first of all, I'm going to show my open circle, and I'm going to show it kind of exaggerated. 0, 1 here is open. Okay, but -1, 2 is just a normal point. -2, 5 is just a normal point. So notice, if you kind of draw this part or this piece, it looks like a part of a parabola. By the way, look at the pattern. That is a parabola, right? An x-squared equation is a parabola. Okay, so let's do a second chart where we only choose things that are greater than or equal to 0. Okay, and by the way, we're splitting them up based on what we have here. Okay, so if we pick some things that are greater than or equal to 0, so let's just pick 0, 1, and 2. Okay, 0 is equal to 0, and then we picked a couple things bigger than 0. Notice this is a really kind of uninteresting function. The answer to all of these is just steady at 1. So what this is telling you is that this graph is steady at 1. Okay, notice though that this 0, 1 lays on top of this what we thought was an open circle, so it's actually going to close it up because this represents a closed circle. So sometimes piecewise functions connect like this one, and then sometimes they're like the handouts that we've had over the past couple weeks where they're completely disjointed. Okay, but notice this is 2 patterns, right? It's a parabola pattern for a while, and then it switches to a constant line pattern. And if you look at the equations at the beginning, we clearly have a parabola function followed by a constant line function after that. Okay, so that's just kind of a bit of review. You may or may not find a whole lot of questions in this section that cover that. I just wanted to make sure that we were all on the same page with graphing piecewise functions.